Hey everybody, your Friendly Math Tutor here with another lesson. Today we're going to jump into Unit 5, Analytical Applications of Derivatives. This is going to be part 1. So if you saw the last two videos, we split Unit 4 up into two parts, and I did it differently. The first lesson, I covered all the topics, and then the second lesson, I just kind of went deeper with some examples. This topic has a lot of, this unit has a lot of topics. So the way I'm going to do this one is I'm literally just going to cover half of them in this video, and then next week will be the other half, all right? So as always, please check out our Patreon, our TikTok, our Instagram, our Facebook. All of that will have more videos that'll be related to this unit this week and next week, as we're going to take 2 weeks to cover Unit 5, as I just explained. And like, subscribe, do all the things that you know to do online. We're kind of everywhere, and we're just going to keep doing this AP Calc course until May, and then hopefully it lives on past that, and you can kind of use this. Anybody can use this any year to get ready for the AP Calc test. All right, so let's dive in. So last week we talked about contextual applications, things like related rates. But this week we took a look at analytical applications. So we're really going to be analyzing, like, what are the derivatives? What do they tell us? And we start with the mean value theorem. So the mean value theorem, first of all, we can only use it if there are two things are true. If our function is continuous on the closed interval a to b, and if f of x is differentiable on the closed interval from a to b. So if we look at this function, a is here, we go to b here. It is definitely continuous and differentiable. That was something we talked about in another video. I don't see any holes, jumps, or asymptotes, nor do I see any corners or cusps. So we're all good. So because of this, what the mean value theorem says is that on the interval a to b, there has to be a c such that this is true. F of b minus f of a all over b minus a is equal to f prime of c. That a c definitely exists on this interval where this is true. And you might say to yourself, okay, well, what does that mean? Well, graphically, it means this. F of b minus f of a over b minus a. That is the average rate of change. We've talked about this in a couple of other videos. The average rate of change, or it's the slope of the secant line. It's an Algebra 1 concept. It's the slope through 2 points. It's something that you've known for years, that you learned way back in Algebra 1 or probably even pre-algebra, right? Rise over run, slope, 2 points. Well, this just represents the slope of the secant line that connects this point and this point. So the slope of that line is this value here. It's saying that if I take the derivative, now the derivative is an instantaneous rate of change. You can't do that in algebra. You need calculus. When you take the derivative, you are finding the slope through 1 point on a function. So it's instantaneously how it's changing, not just how it's changing on average over an interval. It's saying that somewhere when you take the derivative, so remember the derivative is the slope of the tangent line. Somewhere along here, when you take the derivative and you find the slope of the tangent line, it will equal the slope of that line. Two equal slopes are lines that are parallel. So it's really easy to see that as long as this thing doesn't jump or have a break in it or do any kind of like corner or cusp, as long as that doesn't happen, which we've guaranteed by these two stipulations, that somewhere along there, let's say here, I can draw a tangent line that is parallel to the secant line. That's all it says, is that it guarantees that there is a tangent line that has the same slope as the secant line, and that value has to be between A and B. All right, that's all the mean value theorem is saying. It looks more complicated than it is. And in action, we're going to take a look at an example. All right, so let's say we have x squared minus 3x minus 2 on this interval, and we want to find the value or values of c. It guarantees that there's at least one value. There could be more than one. And the way we do that is, let's first find the slope of our secant line. So that's f of 3 minus f of negative 2 all over 3 minus negative 2. That's going to equal the derivative with c substituted in. The derivative is 2x minus 3, so that's going to be 2c minus 3. That is f prime of c. All right, a lot of times we just keep x there. I'm just doing it, mathematically correctly. But if you just leave an x in here, I think that's probably okay. You'll still get the right answer. But I'm going to change it to c just to make it, kind of mathematically appropriate. So f of 3. Well, just plug in 3, so we get 9 minus 9 is 0. That's negative 2. F of negative 2 is 4 plus 6 is 10 minus 2 is 8. 3 minus negative 2 is 5, equals 2c minus 3. This is negative 10 over 5 is negative 2 equals 2c minus 3. Add 3 over, 1 equals 2c, and c is going to simply equal 1/2, and then we can just double check that 1/2 is in fact between negative 2 and 3, which is guaranteed by the mean value theorem, and also something that I skipped that I should have mentioned in the beginning. Don't even start the problem unless this is both continuous and differentiable, but we know that it's a polynomial, so it's going to be continuous and differentiable because it's not going to have any suspicious points for either type, all right? So that is an example of how we use the mean value theorem to find the specific value that will make the slope of the tangent line equal to the slope of the secant line, okay? All right, the other thing that I want to go over in the beginning here is just some vocabulary related to extrema. So we're going to be learning things like local extremes and global or absolute extremes. Or the other word for local is relative. I'm going to choose to use local and absolute, but just understand that relative is the same as local and global is the same as absolute. So your teachers in your class might be using the different words. Again, I'm just going to use local and absolute. So if we just take a look at this, the first thing we want to look at is we've got an interval here. So we're going from this x value, which I'll call A, to this x value, which I'll call B. So we're typically looking at an interval from A to B. And along that interval, we've got some endpoints. So here is what I would call an endpoint, and here is another endpoint. So they are just the places where this function on the interval where it starts and then where it stops. Then along the way, we've got this value, this value, this value, and that value. All of those values I'm going to call critical numbers. Or if you look at the full point, they're critical points. All right, I don't want to put them here because they're going to be named. They're also going to be something else. But these are critical numbers. So here, 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 and here. They are wherever we have possible horizontal tangent lines, which means the derivative is equal to 0. Or something like this, we have a cusp. So the derivative is undefined. So anywhere the derivative is equal to 0 or undefined, we call a critical number, or if you plug that number in, you can create a critical point, an x and a y value. So then we can classify them. So if we take a look at this one, this point is lower than all the points around it in its neighborhood, so we call it a local min. Whoops. This point is higher than all the points right in its immediate neighborhood, so we call that a local max. And same thing, this one is lower than everything around it, so we call it a local min. And this one is higher than everything around it, we call it a local max. Okay, so you can have multiple local mins, multiple local maxes. And then the other important thing is this idea of an absolute min or absolute max. What we do is for an absolute minimum value, we look at the lowest point on the graph. Well, as far as on our interval goes, the lowest point on the graph is this point down here. So this, being an endpoint, is also an absolute min. And then I look at the highest point. This point is the highest point. So it's a local max and it's an absolute max. All right, this max is higher than this max, which is higher than either of the endpoints. So that's just some vocabulary: local min, local max, absolute min, critical numbers, and then endpoints. So we're going to do more with that moving forward, but I just wanted to do a quick introduction to our vocabulary to make sure we're kind of on the same page here. Okay? All right, let's move on to absolute extrema. So we had just mentioned that in the last part with the vocabulary. We're going to focus in on absolute maximum and absolute minimum. And what we're going to do is look at it graphically. So on a specific interval, we're going to look at the absolute highest value and the absolute lowest value. So for right now, the way that this is set up, the absolute lowest value is this. So this is the absolute minimum. And then as we go, the absolute highest value is this. So the absolute maximum. Notice where they occurred. They occurred at the endpoints, all right? On this one, they happen to be the highest value is the second endpoint and the lowest value is the first endpoint. So then what I'm going to do is, let's say that we have a different function, or I'm sorry, we have the same function, but we change the A and B. So I'm going to use a different color here. So let's say we make A here and B here. So I'm going to trace out that part of it. So I've taken the exact same function, but I've shortened the interval. So now notice that the absolute max is here, and the absolute min is here. So what just happened was the absolute max is occurring at a local max, and the absolute min is occurring at a local min. So notice that none of the only way that we could have an endpoint be an answer is if the endpoint is higher than any of the local maxes. And the only way that the absolute min could occur at an endpoint is if it's lower than any of the absolute, lower than the local minimum. But if it's not, then our absolute max and min are going to occur at local maxes and mins. And we could have a combination of this. We could have started here and then stopped here. So our absolute min would be here and our absolute max would be there. So basically the whole point of this is, if you just imagine messing with the interval, an absolute maximum or minimum can only occur at a critical number or an endpoint. So it leads to something called the candidates test. All right. And so what the candidates test says, that basically on an interval, you obviously have an infinite number of points. And what we want to do is we want to find the highest and the lowest. So we want to be able to figure out which point is the highest and which is the lowest, but without a graph. So we're going to do an example of one where we don't have a graph to look at. So we need to take these infinite number of points between A and B, and we need to shrink it down to what we call candidates for an absolute max or min. So our candidates test says that all we have to do is test the endpoint and test the critical numbers. And of those, now we have a much smaller collection of a finite number of numbers, usually just 3 or 4 or maybe 5 or 6, not many. We can test those and plug them into the original, and knowing that they're the only candidates for an absolute maximum, we'll at least be able to compare those values, all right? So we take an infinite number of points and we see that we can shrink that down to just the endpoints, and the critical numbers are the only possible places that an absolute max or an absolute minimum could occur. So let's take a look at an example of that. So endpoints. So what I'm going to do is I'm going to make a little table here. And in that table, I'm going to say, well, I know I need to test the endpoints. Well, I know them right away. That's -4 and 2. And then, are there any critical numbers between -4 and 2? Well, critical numbers, we just looked at that graphically. But we saw that critical numbers are wherever the derivative is 0 or undefined. So let's find the derivative. And let's set that equal to 0. It's not undefined anywhere, no denominators or anything to worry about there. So let's see where this equals 0. So I can divide everything by 6. So x squared plus x minus 2 equals 0. I can factor that to x plus 2x minus 1. So I get x equals -2 and x equals 1. They are the critical numbers. So I need to test there too. So -2 and +1. So these 4 values are now our candidates. They are the only possible values between -4 and 2 that could result in an absolute minimum value or an absolute maximum value. So I did this already. I plugged these in. But what I'm going to do is I'm going to be plugging these in to the original, not to the derivative. I want to know which one has the highest value of the original function and which one has the lowest value. So if you substitute -4 into this, you get -28. If you substitute -2, you get +24. If you substitute 1, you get -3. And if you substitute 2, you get 8. Right? So they are our values. So what this means is you have an absolute min at the smallest of these values is -28. So it occurs at -4, -28. And you have an absolute max at, well, the largest of all these values is 24. So that's at -2, 24. Sometimes they'll ask you where they occur at, so that could be just the x value or the whole point, or if they just ask for the absolute minimum value, that's only the y value. So the lowest value on this function is -28, and the highest value is 24 on this interval. All right, so there's different ways that it could be asked, but that is how we use the candidates test to narrow down an infinite number of numbers to a finite number of numbers, and then we just compare them to each other to find the absolute maximum value and the absolute minimum value on a specific interval. Okay? Let's move on. So now we take a look at the first derivative test. And to understand the first derivative test, I want to just take a look at, again, this graphically. So the first derivative tells us the slope of the tangent line at any point. So what that leads to is the fact that when the first derivative is positive, we have a positive slope. And when the first derivative is negative, we have a negative slope. So that tells me that if I have a positive slope at a specific point, then that means the function itself must be increasing. So anywhere the function, when I draw it from left to right, that it's moving upward, that means that it's increasing, and it's increasing when the first derivative is positive. And then as we keep going, if I'm drawing it downward, that means there's negative slopes. At every single point we have negative slopes. So negative would mean the first derivative is a negative sign. So wherever the first derivative is positive, the original function, so this is important, this is f of x. In next week's video, we'll talk about the connection between the graphs of the first derivative and the second derivative and the original function. For right now, we're just looking at the original function. When the original function is moving upward, the first derivative is positive. When it's moving downward, the first derivative is negative. And what that leads to, so basically on this little interval here, the first derivative is negative. And then, whoops, positive. What am I saying? This is moving upward. Then here it's moving downward, so the first derivative would be less than 0. And then it's moving upward again, so the first derivative would be greater than 0 again. So now notice what we have on here. This is a local max, and this is a local min. Well, local max is going to occur when it is increasing before it and decreasing after it. Well, that's when the first derivative is positive before it and negative after it. And then a local min is going to occur when it's decreasing before it and increasing after it. So that's when the first derivative is negative before it and positive after it. So now we can develop this idea of a first derivative test to figure out where we have local mins and local maxes without having to look at the graph just given a function. So let me illustrate that here with an example. So the first thing we're going to do is take the derivative. So we get 12x cubed plus 12x squared minus 24x. And then if I want to figure out where there are local mins and maxes, well, local mins and maxes are going to have to occur at critical numbers. We've seen that earlier. Absolute mins and maxes could occur at critical numbers or endpoints, but local mins and maxes have to occur at critical numbers. That's the only places they could occur. Now, we could have critical numbers where they don't occur, but the converse of that is what I was talking about, which is the fact that if you have a local min or max, it must have come from a critical number. So let's find our critical numbers. Let's set this equal to 0. I can divide everything by 12. I can factor out an x. Don't divide by x. If you divide by x, you will lose a solution. So I want to factor out an x, but I can divide by 12 because I have 0 on the other side. But I can't divide by x because x could be 0, and I can't divide by 0. So I get x squared plus x minus 2. I get x plus 2 times x minus 1. So here's what I have. I'm going to make a number line. I'm going to do a bit of a sign analysis. I have 3 critical numbers, 0, -2, and 1. I'm going to put them on the number line, 0, -2, and 1. And what I'm going to do is I'm going to find out on the intervals whether the derivative is positive or negative. So let's pick a number over here to the left of -2, say -3. -3 is going to make this negative, and this negative, and 3 negatives make a negative. So normally on a number line, I'd just put a negative. But since this is the first derivative number line, I personally like to draw a down arrow. And it tells my brain when I look at it, especially when we do second derivative number lines in a little bit, I look at this and that my brain immediately can say, okay, well, yeah, it's negative, but what it's really telling me is that the original function is decreasing. So I like to see that. That's really helpful for me. So then if I go from -2 to 0, let's say I pick -1. Well, -1 is negative, positive, negative. 2 negatives make a positive, and instead of putting a positive, I put an up arrow because, again, the job of the first derivative is to tell me that the original function is increasing or decreasing, so since it's positive, it must be increasing. 0 to 1, say 0.5. I got positive, positive, negative. Well, 1 negative makes it negative, which means, again, the original function is decreasing. And then to the right of 1, I'm going to have, say, I pick 2. Positive, 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 so it's increasing. And now I have a really good visual. If I needed to list out the intervals of increasing or decreasing, it would be decreasing from -∞ to -2 and 0 to 1, not including those numbers, because at those numbers it's not increasing or decreasing. And it's increasing from -2 to 0 and 1 to infinity. But what I really want to do is the first derivative test. I want to classify my critical numbers, -2, 0, and 1, as either local mins or maxes. Well, -2, since it's decreasing to increasing, I can see it. I can just visualize this. This is why I like doing this. I can just visualize this going like that, so this would have to be a local min. 0, again, I can visualize it going up, then down, so I think of this as a local max. And then here, going down, then up, that's a local min again. It is possible to get either decreasing, decreasing, or increasing, increasing. And if that happens, then it's neither. It's not a local min or max. So not all critical numbers are local mins and maxes, but all local mins and maxes are definitely come from critical numbers. And if we wanted to, again, I did this before, we could plug these numbers into the original if in the problem they want the actual coordinates of the local min and max. So in this case, it was -2, -20. I plug that in again to the original. this one was 0.12, and this one was 1.7. So it just depends on what your teacher wants a lot of times, as far as do they want the full coordinate pair, or do they just want to know the x values, or what's the question asking? If it wants the points, the full coordinate pairs, then we would have to again plug it into the original. But when I plugged in these values, I plugged it into the derivative because I wanted to know the sign of the derivative gives me if the original is increasing or decreasing. And then if the original is decreasing to increasing, I get my mins. And if it's increasing to decreasing, I get local maxes. All right. All right. Let's, I think it's time to move on. Okay. So on to our last kind of topic / topics. I want to go over something very important. When I first learned this, I used to use these in the wrong way, interchangeably. And it can lead to some confusion. It also is important to just understand like the semantics of this based off of like a question and what they're really asking you for. It might seem like, oh, this is no big deal, but it is important to understand. There's a big difference between the second derivative test and the intervals of concavity / inflection points. So first, let me just go over, before we even get to that, what we have here is concavity is just how the graph is curved. So if you look at this part of the graph, this is curved downward until we get to like a certain point here, and then it's curved upward. The way it's curved, or the way it's facing, is what we call concavity. This is called concave down, and this is called concave up, all right? What tells us about concavity is the second derivative. So what we just saw in the last segment was that the first derivative, just the job of the first derivative is to tell you whether the original function is increasing or decreasing, and the sign of the first derivative tells us that. For concavity, the sign of the second derivative tells us whether something is concave up or concave down. Now, the sign of the second derivative tells us whether the original f of x function is concave up or concave down. Now, what the second derivative test tells us is it does the same, it gives us the same information or answers the same question as the first derivative test. The first derivative test told us, okay, we've got critical numbers. We are going to classify them into local mins, local maxes, or neither. The second derivative test does the same thing. It takes the critical numbers and it says it's either a local min, local max, or neither. It does it in a different way, but that's its job. The first derivative test and second derivative tests give us the same information, just in a different way. All right, so again, they're both about classifying mins, maxes, and neither based off of different methods. The first method was first derivative test. It told us if it went increasing to decreasing, max, decreasing to increasing, min, increasing, decreasing, neither. So let's illustrate how the second derivative test works. Then we're going to find the intervals of concavity for a different example, and those intervals that we find for the second derivative many times is mistaken as the second derivative test. That is not the second derivative test. The second derivative test looks like this. Find the first derivative, and find the critical numbers of the first derivative. So we call them first order critical numbers. I can divide by 4. Actually, yeah, I want to equal to 0. Divide by 4. Take the x out. Factor completely. All right, difference of 2 squares. So I got 3 critical numbers. The first derivative test had us do the first derivative number line. This is the confusion because then we think second derivative test, we do a second derivative number line, but we don't. First derivative test, we do a number line, but we don't for the second derivative test. Second derivative test looks like this. If we have already known critical numbers, right, then let's say if we look at this graph right here, if this is a known critical number, but we don't know what it looks like, but right now we're looking at some graph, this is concave down. So if something is a known critical number and it's concave down, you're going to have a local max. Or if you have a known critical number and it's concave up, you're going to have a local min. Well, so instead of doing a first derivative number line and think about increasing, decreasing, we just look at it in a different way. We just say, okay, well, if I can find the second derivative at these values, and if the second derivative is positive at an already known first order critical number, then it must be if it's positive, it's concave up, it must be a minimum. And if it's negative, meaning concave down, it must be a maximum. So it's a different way of classifying these as local mins or maxes. So I'm going to find the second derivative. So I'm going to go back to this one, and I'm going to get 12x squared minus 4. So I'm going to do this. I'm going to take the second derivative at 0, and I get negative 4. So what that tells me is this. First of all, it's already classified as a critical number. I can't just do this for any point that I want. But since it's already a critical number, and combined with the fact that it's concave down, the 4 doesn't matter. It's the fact that it's negative. So something, and again, that's concave down and it's a critical number has to be a local max. So that means 0 is a local max. Then I can do second derivative at 1. But when I plug in the second derivative at 1, I get 12 minus 4 is 8. Well, I don't care about the 8. I care that it's positive. Well, if it's positive, the second derivative is positive means concave up. So if it's a critical number, it's sitting at the bottom of that concave up, which means it's a local min. And finally, let's do negative 1. So f double prime of negative 1 is, well, negative 1 squared is the same as 1 squared, so I'm also going to get 8. So if it's positive, it's again a local min. All right, so that's the second derivative test. We don't do a second derivative number line for the second derivative test. We do a first derivative number line for the first derivative test. But second derivative test takes first order critical numbers, throws them into the second derivative. When you get a negative value, it's a local max because it's concave down. When you get a positive value, it's a local min because it's concave up, and that's what a min would look like. All right, so it's important to kind of make that connection. Now, what sometimes gets conflated with the second derivative test is finding the intervals of concavity in something called inflection points. So again, we've got concave down, concave up. Where it changes concavity is what we call an inflection point. Well, if we want to know the intervals of concavity and the inflection points, we're just going to go straight to the second derivative. I mean, we're going to find the first derivative first, but we're not going to do anything with it, like find the critical numbers of the first derivative. We're just going to get to the second derivative and then do the number line like we did for the first derivative test, which is why, again, a lot of times people think of that as the second derivative test, but it's not. It's just finding concavity. It's just analyzing the second derivative using sign analysis. So let's see how that works. So the first derivative is 12x cubed minus 12x squared. And the second derivative, I'm going to go right to that, is 36x squared minus 24x. Now I do want to find the zeros of that. So we call these the second order critical numbers. This is simply just because I'm doing a sign analysis and I just need to know where the zeros are. We did this back in pre-calc when we did nonlinear inequalities. We have to just find out where those zeros are. It just happens to be we're analyzing the second derivative, so we need to know where that's 0. I can divide everything by 12, so I get 3x squared minus 2x equals 0. Take out an x, so x times 3x minus 2 equals 0. So 0 is one of my second order critical numbers, and then 2/3 is the other one. And then I can use this last one and do a pretty easy sign analysis. So if I plug in a negative number, I'm going to have a negative times a negative, which is a positive. But this is, again, just something that I do. You can write a plus there, and that's fine. But I like to write, since it's positive, it represents concave up. So then my brain sees that and goes, okay, the original function's concave up there. From 0 to 2/3, let's say I pick 1/3. That's going to be positive times a negative, so it's going to be concave down. So I'm going to draw just a little concave down graph to kind of tell me that that's what that information represents. And let's say I plug in 1, I'm going to get positive times positive, so I'm going to have concave up. So this means it's concave up. And when I say it's really important to know I'm talking about the original function. The sign of the second derivative describes the original function. And that's going to be concave up from negative infinity to 0. And then again from 2/3 to infinity. and then it's going to be concave down wherever the second derivative is negative, which is between 0 and 2/3. And then we have both of these we would call points of inflection, because the derivative changed concavity and they're also not vertical asymptotes. If you have vertical asymptotes here and they could change concavity and they wouldn't be points of inflection because vertical asymptotes aren't points. We will talk about that more next week. But for now, we have just a polynomial, so no vertical asymptotes, none of that to worry about. So changing concavity is going to lead to what's called a point of inflection. And on a graph, it's going to look like this. It's going to be the exact point where it changes from concave down to concave up. At that point, it doesn't have concavity, which is why we didn't include them here. But we would say, and if we wanted to find the full points, we could plug them into the original. I did not do that, but 0, you can see, would be 0, 0. You could plug in 2/3 if you wanted to get the full point if we were going to graph it. So again, that's something we'll do more next week. We'll kind of put all this together and we'll do curve sketching. We'll also take a look at some optimization, some applied problems of this concept. So that's all for next week's video. So that concludes this week. We got part 1 of Analytical Applications of Derivatives. As always, like this video, subscribe to our channel, check out our TikTok, Instagram, and Facebook. Also check out Patreon. I got some more cool things going on there as we get closer to this upcoming AP test. All right. I hope that was helpful.